In Chapter 7, we are looking at geometric applications to the definite integral. In Lesson 1, we're going to focus on the area bounded between two curves. So in this graph illustration, I'm going to bound these between x equals a and x equals b. And we're going to consider the area of the region bounded between the two curves f of x and g of x. The way I'd like you to think of this is we need to add up a bunch of geometric shapes. Inside this region, I'm going to draw a rectangle. Notice that the top of the rectangle is the red function, and the bottom of the rectangle is the green function. And that will be true no matter where I draw the rectangle. If I drew it over here, the top is still red and the bottom is still green. And so the area bounded between the graphs of f of x and g of x is going to be approximately the sum of these rectangles. Now the width of each rectangle is going to be some partition change in x, but the height of each rectangle is going to be the difference of f of x and g of x. And the width is going to be change in x. So if I wanted to find the area of the region, the actual area, I'm going to do the infinite sum from x equals a to x equals b of the height, which is f of x minus g of x, the height of the rectangle, times the width of every rectangle, dx. So the same idea is going to apply here. We have two functions, f of x on top and g of x is on the bottom. These are going to be bounded again by some x equals a and x equals b. I need to find a geometric shape that I want to sum in effort to find the area bounded between these two curves. This one appears tricky because it crosses the x-axis at a variety of points, but it turns out that that doesn't matter because the height of every rectangle is still the difference between f of x and g of x. So see, I draw this one and the top is red, the bottom is green. That's going to be true over here. Top is red, bottom is green. To give you just a sense of that, let's pick some hypothetical values. Suppose that this value here is a 5 and the value down here is a -3. So the top of it's going to be 5 and the bottom is -3. So the height of that rectangle is 5 minus -3. The height is still 8. Over here, the top, let's say, is the -3 and the bottom is, let's say, -7. To find the height of this particular rectangle, -3 minus a -7 will equal 4. So in effort to find the height of a rectangle, it's always the top of it minus the bottom of it. And so my area of the region bounded between f of x and g of x from a to b is going to be the infinite sum of rectangles from a to b, where all of the heights are f of x minus g of x, regardless of its location above or below the x-axis. And the width of each of them is still dx. So I want you to see from this that no matter where they're located, the area is always the infinite sum of rectangles, the top function minus the bottom function. In our final illustration of the first page, I want to show you what happens when two curves intersect, as you see here. I'm interested in finding the area bounded between the curves, so I'm going to shade that here, and I'll use a different color over here. In the gray shaded region, we have rectangles whose top is the red and the bottom is green, like this, but then these two are going to change after they intersect so that the top is now green and the bottom is now red. So what you would need to do in this type of situation is find the point of intersection. Let's label that x equals c, and then we'll express the area here. So the area then is going to be the infinite sum or integral from a to c of red f of x minus green g of x, that's the height of all the rectangles in the gray shaded region, dx, plus the integral from c to b, and I'll now switch that, g of x minus f of x dx. All of these examples show that if we infinitely sum rectangles, we will find the area of bounded regions. In example number 1, we want to find the area bounded between y equals x squared and y equals the square root of x. I guess it behooves us to figure out which one is which. The red shape, the one on the top, is actually the square root of x, while the green colored one is y equals x squared. And we want to find the area bounded between these two. The first thing I'd like you to do is take a very light shade of color and shade in the area of interest. The next thing I'll have you do, please, is you're going to draw a rectangle that fits in the region. In this case, I'll draw a vertical rectangle like we did in the introduction, such that the top is red and the bottom is green, as you see here. This problem did not tell us the bounds. We know that they're going to intersect at 0. We also have to figure out where they're going to intersect over here. Now, if you can't figure that out in your mind, you would come over and set the two functions equal to each other. And doing the algebra, we would learn that they intersect at x equals 0 and x equals 1. So we're going to focus on the setup. So the area is the integral from the first rectangle at 0 to the last rectangle at 1. Do you see that? The first rectangle is down here and the last rectangle is here, and all the rectangles in between. So the top of this is going to be the square root of x. The bottom of the rectangle is going to be x squared. That quantity represents the height of every rectangle, and the width is dx. And that finishes the setup of example 1. In example number 2, we want to find the area bounded between y plus x squared equals 6 and y plus 2x minus 3 equals 0. I'm going to first off shade the region of interest. So all that shaded region, do that lightly with your pencil. Then we want to draw the rectangle. So the rectangle, again, is this vertical rectangle where the top touches red and the bottom touches green. We make sure that's going to be true at every point in the region, no matter where I draw the rectangle. So I drew a couple there. It will also be in our interest to write each one of these equations as a function, 6 minus x squared, which is clearly a parabola, and we'll write this as y equals 3 minus 2x, clearly the line. So I'll circle this one with the green color, and I'll circle the other with the red color. Tells me top and bottom of the respective rectangles. So now our area is from the first rectangle at, we got to figure out what that is. So I'm going to set 6 minus x squared equal to 3 minus 2x. Found here. So from the first rectangle, which occurs at x equals -1, to the last rectangle, which occurs at 3, top of the rectangle, 6 minus x squared. I'll put that in parentheses. The bottom of the rectangle is the quantity 3 minus 2x. That entire expression represents the height of the rectangle. The width is dx, completing the setup for finding the area of the shaded region R bounded between the two curves. In example number 3, we have 3 equations: y equals x plus 6, y equals x cubed, and y equals -x over 2, and we want to find the area bounded between these 3. I'm going to lightly shade the region of interest. But you might notice something here. In the second quadrant, the top of any rectangle would be pink and the bottom would be orange. That'll be true in this region here. Then the other shaded region, which is still in gray, has a different top and bottom. So I'm ready to draw some rectangles. I have rectangles here, but then I'm going to have different rectangles, so I'll choose a different color. I'll have different rectangles in this region, and it changes because the bottom of the rectangles is not always the same. Let's identify which function is which. So the y equals x plus 6 is clearly linear with a y-intercept of 6. The other line we have is this one here with a negative slope, so that'll be the bottom. That'll be this graph here. And then finally we have the cubic, which we have in this blue color. The two lines will intersect each other at x equals -4. The pink line and the cubic will intersect at x equals 2. And the beige line will intersect the cubic at x equals 0. We're ready to find the area of the shaded region. So the area equals the integral from the first rectangle at -4 to the last rectangle of the darker shaded region, which is at 0. The top of each one of those rectangles is x minus 6, and the bottom of each one of those rectangles is -x over 2. dx. Now I need to add some more area. That's the areas to the right, and those start with rectangles at 0 and end with rectangles at 2. Each one of those has a height of still x plus 6, but then has a bottom of x cubed. And widths are always dx in these first several examples. You could also notice that when I subtract a negative, that can become plus. But for now, I'll keep it like this so I can recognize the form. Example number 4 offers something very different than the other ones. Let's take a look at this equation here. X equals 2y cubed minus y to the power of 4. Notice that that is not a function. If I were to graph that, x would be a quartic, a 4th degree. So I'm going to trace that here, coming down like this, coming over and off like that. That is not a function of x, but x is a function of y, and that's going to come into play here. The other equation, x equals y squared minus 2x, is a quadratic, and that will look like this. Okay, I want to show you why the type of rectangle that you draw is very, very important. Suppose I draw the rectangle vertical, like we've been doing in all the examples so far. I want you to see that that is not a legal rectangle. That is not a legal rectangle because if we look at the top of the rectangle, it's the quartic pink function. The bottom of the rectangle is still the quartic pink function. The top and bottom of the rectangle cannot be the same function because it would be a quantity of 0. So what I'd like to show you here is that every rectangle we draw must be horizontal. Now, why is that a must? That's a must because every rectangle that I draw that is horizontal in nature has a very special feature, and that feature is that the top, I'm calling top the rightmost part of the rectangle, is always one particular function, the pink, and the bottom of the rectangle or left part of the rectangle is always the blue. And that will be the same no matter where I draw it in that shaded region. The top is always one curve, one equation, this one here, and the bottom is always the other equation. Okay, so we're ready to find this area. I think you can see on the graph itself these points of intersection. They intersect at y equals 0, and then they also intersect at y equals 2. Now, if you didn't know that, you can certainly set these two equations, 2y cubed minus y to the 4th equal to y squared minus 2y. Oh me, this should have been y all along. Hopefully you picked that up. And we would have found that y equals 0 and 2. I'm ready to set up to find the area. So now, the rectangles start at the bottom. The rectangles start at y equals 0. And they finish at y equals 2. And then the height of the rectangle, kind of interesting because it's on its side, we call the topmost the rightmost, or more positive most, and that would be the equation 2y cubed minus y to the fourth. That is the top of each rectangle. The bottom of each rectangle is the y squared minus 2y. And then the width of each of these rectangles is no longer dx, but dy. See, these partitions along here have an increment in the y direction. The next two examples are calculator active, so you'll want to pull out your calculator and get ready to find the answers here. I have two functions. F of x is the cosine, and g of x is the quadratic, as you see here. Take a moment and enter those into your calculator as y1 and y2 respectively. You'll want to make sure you're in radians, of course. Once you have those entered into your calculator, you'll want to graph them to get a picture similar to the one that you see here. Our first goal is to find the points of intersection so that I can find the area of the region bounded between the two graphs. Perhaps I should shade that region first. There we go. Let's find these points of intersection where the two functions intersect. Take a moment to do that. I'm going to label the first point of intersection A and the second point of intersection x equals b. Once you find these, hopefully you found A to be negative 1.900. Remember, we round to 3 decimal places. And the intersection x equals b will be the value 1.408. Make sure you're getting these values, practicing the keystrokes that are used to find them. Now I have to set up the integral to find the area of the shaded region. Perhaps I'll draw a rectangle here. There we go. Do you see which one is on the top? The one on top is the cosine. And the one on the bottom is the quadratic. There we go. So our area is going to be from the first rectangle, which occurs at little a, to the last rectangle, which occurs at b. See, it's okay that I use a and b because I've defined them on my paper. Next, I want to show the height of every rectangle, which is f of x minus g of x. I can write f of x and g of x because, again, those are labeled on my paper. I do not have to rewrite their values. The width is dx. Now I want to evaluate this on the calculator. If you do it right, the answer comes out to be 6.935. Perhaps here we'll review how to do that in your calculator. I will take the integral of, I'll call up function y1 of x, that should be my cosine function. Then I'll take away y2 of x, which is my parabola. That's the integrand, and I'll do that with respect to x, and I'll take that from negative 1.900 out to the 1.408. Upon pressing enter, it will yield the answer 6.935. Example number 6, the last one here. This is again calculator active, so I'd like you to take a moment and try to find the answer of the area bounded between the graphs of f of x and g of x. Of course, that's bounded between x equals 0, so that's here, and x equals 1 point, and there's a lot of decimals, so that's out here. So only everything inside these vertical bands and bounded between the graphs of f of x and g of x. Press pause, find the answer, then we'll go over it. One of the tricky parts about the problem is just figuring out which one is f of x and which one is g of x. The f of x function is this cosine, and that's going to come out like this. Then we have g of x, which is a sine function. They're both sinusoidal. That one has an intercept higher than the cosine curve. And that comes like this. It's actually going to intersect, come down, and then back up. Remind you though, we need to be bounded between x equals 0 and x equals 1.48858. So that particular bounded region then is going to be just here and here and here, nothing to the left of the y-axis. Hopefully you see or saw that since these intersected, we have to find that point of intersection. I'll call that point of intersection C. And these two curves intersect at C equals 0.420. That's where the behavior of the rectangles will change. So our area is going to be the integral from 0 to 0.420. The top of the curve is the green or sine, and the bottom is the red or cosine. I will write g of x minus f of x to represent those heights of those rectangles and width. Now I have to add to that the other region, which is going to go from 0.420 to 1.48858. Now they swap. This time f of x is on the top and g of x is on the bottom, and the width of dx. If you've entered it correctly in your calculator, you'll get 0.860 is the correct answer. And perhaps you're wondering to yourself, wait a minute here. How did he know which one was g of x and which one was f of x? There are a couple ways to do that. One way is to graph each one separately. Perhaps this information here would let you know that we're going to get more revolutions in a smaller x range. See, the cosine is going to go slowly, the red, but this is going to have or give us a smaller period. Another way you could have determined it was calculate y1 at 0, which is clearly going to be 1, but then you could have calculated y2 at 0, which is this one here, and that you would have found was greater than 1, letting you know which one was which. To finish the lesson, I'd like you to go back to example number 1. The focus of the non-calculator problems was setting up the integral, but I would like to finish by solving a couple of them just so that we stay fresh, because in the homework I am going to have you find the area. So let's review how we might solve one of these. To find the definite integral, first I need the antiderivative. I can think of this as x to the 1/2 power. The antiderivative is x to the 3/2 power divided by 3/2 or times 2/3. Minus the antiderivative here is x cubed over 3. By the fundamental theorem of calculus, I will take that from 0 to 1. I will first plug in the 1, which gives me 2/3 minus 1/3. Then I will subtract the values when plugging in 0, which come out to be 0. So the answer to this first area was 1/3. If I do that for the second example, example number 2, then it is in my best interest to simplify first. So I will distribute here. So this is going to be the integral from -1 to 3, 6 minus x squared minus 3 plus 2x dx, which is then -1 to 3. I will look at my constants, so I have a 3, 6 minus 3 is 3, plus a 2x minus x squared dx. It is time to find the antiderivative, so we have 3x plus 2x squared over 2, 2's cancel out, so just x squared, minus x cubed over 3, I will do that now from -1 to 3. When I plug in the 3, that will give me 9 plus 9 minus 27 over 3. When I plug in the -1, that will give me -3 plus 1 plus 1/3. Now I'm left to do the arithmetic, and if I did the arithmetic correctly, I should have got an area of 32/3. The answer to number 3, the actual area, is 22. Feel free to check that out. In example 4, this one was a little bit brutal, but I got 44 over 15. That one's a little bit of an arithmetic nightmare. That is the end of Lesson 1.